Chapter 6 in class exercise 4 problem 6.64. Determine the force P required to hold the 150 kilogram crate in equilibrium. So mass of this crate is 150 kilograms, so its weight W is 150 multiplied by 9.81. Okay, so that is 1471.5 newtons. Remember that force is in Newton. That's why we need to convert this kilograms into Newton. So multiply that with 9.81. Now that weight is being supported by pulley A, which in turn is being supported by pulley C, and this is where the force P is applied. So we need to calculate how much force do we need to apply in order to hold this 1471 newtons of crate in equilibrium. So we first draw the free body diagram for A. So for pulley A, let's call this tension here TA. So each one of this tension is TA, and that supports W. Therefore, we can, using equation of equilibrium along vertical direction, we can say that sigma F in vertical direction is 0, going up is positive. Therefore, 2 times TA minus W is equal to 0. Therefore, TA is W by 2, okay, which is 1471 by 2, that's 735.75 newtons. Now that this one is 700 newtons, that 700 Newton actually goes to C, which is then further split and by two cables and shared and supported by these two cables here. So if this is P, we can say that this is also P. So 2 times P is supporting this TA. So now next step is draw free body diagram for C, where this is TA and that's being supported by 2 times P. Okay, for this case, because this coordinate system is at an angle, we will create our new coordinate system where y dash is at an angle and it's parallel to the angle of this cable. So we don't have to find any sine and cosine components. We can just say that TA is in the direction of y dash. So sum of forces along y dash direction is equal to 0 because the system is in equilibrium. So TA is positive, so it's going up, minus 2P is equal to 0. Therefore, P is equal to TA divided by 2, which is 367.8 newtons. Okay, so let's look at the entire solution one more time. So 150 kilogram crate is being supported by two cables, so each one of them carries supports half of the weight, so that's 735, which in turn is being supported by two cables, so each one of that carries half of TA, which is 367.8 newtons. So we need to apply 1/4 of the weight of the crate to support the system is in equilibrium. Now we'll work on the last problem from this in-class exercise, which is problem related to machines. Problem 6.104. So the hydraulic crane is used to lift the 1400-pound load. Determine the forces in the hydraulic cylinder AB, which is this AB, and the forces in the link AC and AD, so here and here, when the load is held in this position zone. So the system is in equilibrium and this is 1400 pound, and we would like to know what are the forces in link CD, link AD, and hydraulic cylinder AB. So the way we approach this problem is we have to draw, because this is related to machine and the members are multi-force members, so we will draw two different free body diagrams. First, we will draw the free body diagram only for this arm. So we will disconnect this arm, include only joint C, joint D, and everything on the right side of it. So we just draw free body diagram for this cantilever arm along with the load and joint C and D. So here is that free body diagram where W is 1400 acting down. At pin D or joint D, we have support reaction dx and dy. horizontal and vertical support reactions. This is X, this is Y. That's our coordinate system. Now at joint C, we have this link AC which is connected. So there is force along link AC, which is FCA. And yeah, this is the applied load, and this angle here is 60 degrees, and the distance between C and D is 1 foot. So FCA has two components, FCA cosine 60, which goes along members CD because cosine closes the angle, and the other one is FCA sine 60, which is this. So the perpendicular distance between C and D is 1 foot. So FCA sine 60 multiplied by 1 exerts counterclockwise moment at D. So we will write the sum, we will apply the equation of equilibrium. Sum of moments at D is equal to 0 and counterclockwise is positive. So we don't need to consider the moment of dx and dy about D because they both pass through D. So the only moment that we need to include is FCA sine 60. Not cosine 60 as well because cosine 60 also passes through D. So it's FCA sine 60 multiplied by 1. So this is force multiplied by distance and moment because of 1400 about D. So it's this moment is clockwise about D. So that's 1400 multiplied by 8 and that's negative equals 0 because the system is in equilibrium, and that gives us the value of FCA, which is 12.93 kilopound. It's actually 12,000 pounds, so we are writing this in kilopound. Okay, so we have solved for force in member CA. Now we will draw the, now let's go back here and look at the problem. Now we will draw the free body diagram for joint A and solve for the unknown forces in member AC, member AD, and member AB. So here is the free body diagram for joint A. So link AC has the force FCA, which is in tension. So that force was pulling at joint C, so it's also pulling at joint A. So relative to joint A, the force in links AC or CA is 12.93 kilopound. Force along member AD is unknown, and force along cylinder AB is also unknown. This angle is 60 degree and this angle is 70 degree. This is given. So now this is simple like problem from chapter 2 where we have two unknowns at one point and the system is in equilibrium. So we are calculating these two unknowns using equations of equilibrium. So if you like, you can actually redraw that diagram separately. So that I have drawn here where FCA, this value is taken from the previous step and these are unknowns. So we don't know this, we don't know this, and all other angles are given. So to find FAB, we will apply we will sum the forces along y direction. So sum of forces along y direction will include FAB sine 70, which is negative, and FCA sine 60, which is positive. Because we know the value of FCA, we can calculate FAB from that. And when we apply sum of forces in x direction, FCA cosine 60 is in positive direction, and FAD is also in, we have assumed that this is in positive direction, so we will solve FAD from that equation. So let's apply equations of equilibrium along horizontal and vertical direction. So these are the both the diagrams are the same. This is on the actual image and this is redrawn simplified diagram. Okay, so sigma Fy equal to 0, going up is positive. So FCA sine 60 minus FAB sine 70 is equal to 0. Therefore, FAB is equal to FCA sine 60 divided by sine 70. And this is 12.39. We know that. Okay, so we substitute that here and get the value of FAB, which is 11.91 kilopound. Okay, and the last step is to solve for horizontal force. So sigma fx equal to 0. Going right is positive. So FCA cosine 60. This FAB has also horizontal component going this way when we close this angle. So it's minus FAB cosine 70 plus FAD, this one, is equal to 0. From that, we can solve for FAD as minus 2.39 kilopound. So we get the negative answer here. That means this assumption of link AD pulling at joint A is wrong. In the actual sense, link AD is pushing at joint A. That means it's in compression. So the final answer is FAD is equal to 2.39 kilopound compression, not tension. So the true sense for FAD is not this, it's actually the other way. It's pushing at joint A because we get the negative number. Okay, so once again, look at the approach that we have followed. We have drawn two separate free body diagrams, one for the cantilever arm of the machine, and we have applied sum of moments at D and solved for force in link AC. And then we have drawn free body diagram at joint A and solve for the unknown forces FAB and FAD. Okay, thank you.